Uber's entire routing system is, at its core, too slow to work. The textbook algorithm for finding the fastest path, Dijkstra's algorithm, is too computationally expensive to run at Uber's scale in real time. So Uber's engineers had to cheat. And the way they cheated is strangely similar to how ancient ship navigators cheated the limits of the human brain thousands of years earlier. Same shortcut, same insight, completely different centuries. Picture yourself standing at a crossroads. Not two paths, thousands. Every direction splits into more directions, and those split again, spreading out faster than you could ever check by hand. You need to pick the right one, right now. And to make it worse, the paths themselves keep shifting while you stand there deciding. That's not just a thought experiment. It's a problem that has followed humans for thousands of years, in one form or another. How do you find the best route through a system that's too big to fully see and too changeable to fully predict? For most of history, getting this wrong wasn't an inconvenience. It was fatal. A ship that misjudged its course could miss an island entirely and run out of water in open ocean, with no way back. Today, the stakes look different, but the problem hasn't gone away. Every time a car, a delivery, or a shipment needs to get from one place to another, something has to solve this same puzzle, instantly and constantly, because traffic, weather, and conditions never hold still. The tools have changed completely. Stars, satellites, wood, silicon. But underneath all of it sits the same brutal limitation. No mind, and no machine, can check every possible path. Something has to be clever instead of complete. That's the problem both ancient navigators and modern engineers were forced to solve. Long before compasses, charts, or satellites existed, Pacific navigators were crossing thousands of miles of open ocean and finding islands too small to see from more than a few miles away. They did it without a single instrument. What they had instead was a method now known as wayfinding. At the center of it was something called the star compass, a mental map of the sky, dividing the horizon into 32 points, each tied to the rising or setting position of specific stars. A trained navigator memorized which stars rose and set at which points, then used that pattern to hold a course through the night. When clouds blocked the sky, the method didn't fall apart. It simply switched inputs. Ocean swells became the backup system. Islands, even ones far below the horizon, disturbed the pattern of waves around them, bending and reflecting swells in ways a trained navigator could feel through the movement of the canoe itself. Bird behavior added another layer. Certain species, like frigate birds, refused to land on water, so their presence meant land was close. Others, like golden plovers, followed seasonal migration routes that lined up with the very paths people were trying to sail. None of these signals worked alone. That's the part easy to miss. A navigator wasn't reading one clue and trusting it blindly. They were constantly cross-checking stars against swells, swells against wind, wind against the estimated speed and heading of the canoe, built up through hours of continuous observation. It was less like following directions and more like running a live calculation in the head, using the sky and ocean as the input data. This knowledge wasn't written down. Pacific societies passed it person to person through years of direct training because that was the only method of storage available. And it worked at a scale that's hard to fully appreciate today. In 1976, the voyaging canoe sailed 2,500 miles from Hawaii to Tahiti using only these traditional techniques, no instruments, no charts, and reached its target. Since then, the same methods have guided voyages across the wider Pacific, part of a deliberate revival effort by the Polynesian Voyaging Society after the tradition had nearly disappeared during the 20th century. What makes this solution remarkable isn't that it worked once. It's that it was systematic enough to be taught, repeated, and trusted with human lives, across a distance most modern travelers would find disorienting even with a GPS in hand. Now take that same problem and hand it to a company that needs to solve it millions of times a day, in seconds, across entire cities. When Uber calculates a route, the underlying idea sounds simple. The road network gets converted into something closer to a giant connect-the-dots diagram. Every intersection becomes a point. Every road segment becomes a line connecting 2 points, weighted by how long it takes to travel. Finding the fastest route just means finding the shortest path through that diagram. There's a well-known method for solving exactly this kind of problem, called Dijkstra's algorithm, developed in the 1950s. Give it a starting point, an endpoint, and a map of weighted connections, and it will reliably find the shortest path. The problem is scale. The San Francisco Bay Area alone contains roughly 500,000 road intersections. Uber's systems handle something like 500,000 ETA calculations every single second worldwide. Run the textbook algorithm at that size for every single request, and the math stops being fast enough to be useful. The tool that should work in theory becomes too slow in practice. So Uber's engineers didn't try to make the algorithm faster through raw computing power. They changed the approach. Instead of recalculating a route from complete scratch every time, they broke the road network into smaller regions and precomputed the best paths within each one in advance. When a new request comes in, the system mostly just needs to figure out how to move between regions, using those precomputed paths as shortcuts, rather than solving the entire puzzle from zero. It's a way of trading a small amount of accuracy for an enormous amount of speed. On top of that structure sits real-time traffic data. As conditions change, the weights on those road segments get updated continuously. So a route that made sense 5 minutes ago can shift the moment a road backs up. And more recently, Uber added a machine learning layer, called DeepETA, that doesn't replace this system but corrects it. The routing engine produces an estimate based on the map and traffic data, and a separate model predicts how far off that estimate is likely to be, based on patterns learned from real completed trips, then adjusts the number accordingly. None of this happens by exhaustively checking every possible route. It happens by simplifying the map, focusing on the parts of the system most likely to matter, and continuously updating the answer as new information arrives, a structure that, on paper, looks nothing like a wooden canoe crossing the Pacific, but is quietly built around a very similar idea. Strip away the canoe and the code, and what's actually left? In both cases, a mind, biological or artificial, took an overwhelming, chaotic environment and compressed it into something smaller and more manageable. The Polynesian star compass turned the entire night sky into 32 fixed points. Uber's routing engine turns an entire city into a diagram of dots and lines. Neither one is a perfect copy of reality. Both are simplified models, built specifically to make an impossible problem solvable. And in both systems, the simplification wasn't random. It was selective. A navigator didn't try to track every wave in the ocean, only the ones that carried useful information about direction or nearby land. Uber's routing engine doesn't examine every possible route between 2 points. It focuses computation on the routes and regions most likely to matter, using precomputed shortcuts instead of solving from zero each time. Different materials, same underlying move. Ignore almost everything, and pay close attention to the small slice of information that actually changes the answer. The other shared trait is that neither system treats its answer as final. A navigator's read of the stars, swells, and wind was constantly rechecked and adjusted through the night. Uber's routing engine updates its road weights continuously as traffic shifts and layers a prediction model on top to correct its own estimates in real time. In both cases, the answer isn't something solved once and locked in. It's something recalculated over and over for as long as the journey lasts. These similarities aren't a coincidence, and they aren't just a clever metaphor stretched to fit. They show up because both systems were shaped by the same limitation. Too much complexity, not enough capacity to process it directly. When intelligence, of any kind, hits that wall, it tends to respond in a similar way, whether it evolved over generations of trial and error or was engineered over a few years by software teams. That said, the comparison has real limits, and they're worth being honest about. The scale is not remotely similar. A Polynesian navigator was solving for one canoe, one crew, one voyage at a time. Uber's system is solving the same category of problems simultaneously for millions of trips across entire continents every day. The way knowledge moved is different too. Wayfinding was preserved through direct, person-to-person instruction, refined and passed down over generations, which is also why so much of it was nearly lost within a single century of contact with outside navigation tools. Uber's methods, by contrast, live in code and data, updated centrally, and pushed out globally in a matter of minutes. The tolerance for error is different as well. A misjudged course at sea could be unrecoverable, There was often no way to detect a mistake in time to fix it. Uber's system is built to expect small errors constantly and simply corrects for them as new data comes in, using tools like DeepETA to adjust predictions after the fact rather than trying to be perfect the first time. One system had almost no room for failure. The other assumes failure will happen in small amounts and builds correction directly into the process. These differences don't weaken the connection between the two systems. They clarify it. They show why one version of this problem needed decades of oral mastery passed carefully between people, while the other needed data centers, sensors, and machine learning. Different constraints produced different tools, even while solving the same underlying puzzle. And that points to something bigger than navigation. Whenever a system, human or artificial, is faced with more complexity than it can fully process, it doesn't respond by becoming more powerful. It responds by becoming more selective. It builds a simplified model of the world, tracks a small number of signals that actually matter, and keeps updating its answer instead of committing to one for good. That pattern shows up in a Pacific navigator reading the sky and in a routing engine reading traffic data, because it isn't really about ships or apps at all. It's a strategy for operating inside uncertainty, one that has been reinvented independently every time the tools available were completely different, but the underlying problem stayed exactly the same. Every generation thinks it invented a smarter way to handle complexity. But maybe what actually happens is we just keep rediscovering the same trick: simplify the world, track what matters, and keep updating in whatever material we've got on hand at the time, stars and waves, or code and servers. So here's the question I'd actually want to know your answer to. Where else do you think this exact pattern is hiding? Some system you use every day that's secretly solving its problem the same way a 3,000-year-old navigator did? Drop it in the comments. I'll read through them.